Okay, in this video we're looking at trig parametrization. Now, technically, this is nothing new. We do know how to do all this already with normal parametric equations, but it's in a very unfamiliar context, so it's really good to practice trig specifically. We'll be seeing a lot of circles. So just as a reminder notation-wise, this position vector is x with an underline, so that's a vector xt, and each individual piece of this is a scalar. So that one is x and that one is y. So you just got to be really careful. That x is not the same as the x, which is the group of all the coordinates. Anyway, let's see if we can graph this thing and have a look. So I'm going to enter my equation. So 6, well, first of all, we better make sure we're in parametric. So let's just type in F3. When I'm ready, 6 cos of 5t. So use the x button and it'll be t now. And 6 sine of 5t. And we enter that. Make sure you're in radians and we'll get a picture of this. Now with our window, let's just set it to standard and see what happens. Yep, looks pretty good. And if you're not getting the whole circle, you can set your t value differently, but it looks like that t value is big enough. Now this looks like an oval or an ellipse. It is not. It is actually just a perfect circle. It's just your calculator is in like widescreen, so it looks a bit weird because it gets like stretched out with the screen resolution. And we can verify this. So if we go trace at 0, we can see that we get 6, 0 for our first point there. And not to mention that's the initial position, so that's good. And we can get some more points here. So that's 6, 0. Maybe let's try and trace at pi and see if anything interesting happens. So trace at shift pi. So we get -6, 0. So that's good. We got that. And maybe if I trace at another point, so let's try maybe pi over 2. There we go. Well, that's really good. So we're going to get this point up here, which is at 0 and 6. And by actually tracing out those coordinates, you can see that this shape is a circle. It just looks a little bit stretched out on the calculator. So we're just going to draw a circle around there. And that's 6 cos of 5t, 6 sine of 5t. Beautiful. All right, next, find the initial position, which we did. Find the position after pi over 10. So if we go trace and go pi over 10, we should get that top point there. So x of pi over 10 is that top point. So that is 0, 6, just up the top there. And you can see that it's sort of written on the calculator there near where the pink plus is. If you want to do that by hand, you could go like 6 cos of 5 pi over 10. And you could see that you would get 6 times cos of pi over 2, which would be 0. And then the sine one would be 6 times 1. So yeah, it would work. Okay, how long will it take to complete a full revolution? So you can pretty much look at the number here. So 6 cos of 5t and 6 sine of 5t. It works the same as normal trig. So this number here, I think the book likes to call it omega, W. I think that's called omega. I need to brush up on my Greek skills. But the point is, that number there is 5. And the period is 2 pi over that number. So if we want, we can just set our window to something just a bit shy of 2 pi over 5. So t currently goes up to 2 pi. So it's actually doing 5 whole loops, the circle now, and the calculator draws it. But if I go 2 pi over 5, and maybe I can just like take 0.3 or something, just so it's like a little bit less, we should see that it almost draws the whole circle. Yes, it does. And then if I go from my window and go 2 pi over 5 perfectly, it should only just barely draw the whole thing. There we go. And if I go trace and I type 2 pi over 5, then we can see that it does have that right point, and that's a full revolution. So 2 pi over 5 seconds. It's a very quick ice skater. Okay, find the velocity vector. So if x of t is 6 cos of 5t, and 6 sine of 5t. Then we can get the velocity vector just by differentiating it. So velocity is, so cos goes down to sine, so minus 6 sine of 5t. And I guess we're going to times it as well, so minus 30 sine of 5t. 6 times 5 out the front there. And we've got 30 cos of 5t. And hence find the speed. So speed is the modulus of velocity. So this is going to be the square root of minus 30 sine of 5t all squared and 30 cos of 5t all squared. And if we do that, so you're going to get 30 squared as a common factor, you're going to get sine of 5t plus cos of 5t all squared, or each term squared. The sine plus cos is actually just 1. And this is why it's really good to practice the trig parametrization. So it's root of 30 squared, which is 30 meters per second. It's a very quick ice skater. It's not the most realistic problem, but there we go. So that's the speed. Now, you might actually notice that we didn't need a t value. So we never actually used pi over 10. So we are basically always going 30 meters per second. Now, just be really careful, because if this shape was actually an ellipse, you would be speeding up and slowing down along that ellipse. And you can check that using an ellipse example. I would encourage you to think about maybe what you would change on this equation to make it not a circle anymore and turn it into an ellipse.